This is the third tutorial for ENGG 2430A, Probability and Statistics for Engineers. From this week on, we will focus on the probability part of this course. Let's start now. The general formula for the calculation of a probability is like this. We use the size of set A divided by the size of set S. It will give us the probability that event A happens. Here, S is the sample space. It includes all the possible outcomes in an experiment. A is the desired outcome. It should satisfy our requirements on an event. So, in order to calculate the probability of an event, we need to count the size of A and the size of S. Then, how to do the counting? We will introduce some tricks in this tutorial. Let's see an example here. Suppose there are n distinct boards labeled 1, 2, until n. Two players draw in turn until no more boards left. Whoever draws board 1 first wins. What is the probability that the first player wins? In order to solve this problem, we need to find the sample space S and the desired outcome A. For S, it's actually the permutations of 1, 2, until n, representing all the possible assignments of boards to the two players. For example, when n is equal to 3, the sample space S is 1, 2, 3, 1, 3, 2, 2, 1, 3, 2, 3, 1, 3, 1, 2, and 3, 2, 1. For A, since we want to obtain the probability that the first player wins, then board 1 should be at odd positions. So A is the permutations of 1, 2 until n with 1 at odd positions. For example, when n is equal to 3, the desired outcome A is 1, 2, 3, 1, 3, 2, 2, 3, 1, and 3, 2, 1. After describing S and A, we continue to calculate their size. For the size of S, based on the formula of permutation, it is equal to n times n minus 1 times n minus 2 until 1, which is equal to n factorial. For the size of A, remember that we first need to put board 1 at odd positions among the n possible positions. The number of positions satisfying such condition is bracket n over 2. Then for the remaining n minus 1 boards, the total possible assignments of their positions is the permutations of 1 till n minus 1, which is equal to n minus 1 factorial. After obtaining the size of S and A, we find the final probability that the first player draws board 1 and wins. From the result, we find that when n is an even number, the two players have equal probability to win. However, when n is an odd number, the first player has advantages. From this example, we can see that finding the right representation for outcomes is very important. We now use another example to show how to find a good and right representation when doing the counting. Suppose n positive integers are randomly chosen from 0, 1 until k with replacement, while n and k are greater than or equal to 1. What is the probability that the sum of the n integers is k? Similar to the previous problem, we first let A denote the desired event and S the sample space. Then we try some simple cases to see whether we could find a good representation for the counting. When A is equal to 1, S is any number from 0 to k and A is k, so the probability is 1 over k plus 1. When A is equal to 2, S is any two numbers from 0 to k and the two numbers can be the same. In this case, A is the possible pair of integers I and j from S, and also satisfy the condition that I plus j equal to k. With further simplification, we find that A is actually the pair of integers I and k minus I, while I is between 0 and k. So in this case, the size of A is k plus 1 and the size of S is k plus 1 squared. The final probability is 1 over k plus 1. Does this mean that the final result is 1 over k plus 1? Let's continue to see the case when A is equal to 3. When A is equal to 3, we first get the sample space S, and A is a set of three integers with their sum to be k. We further discuss the size of A when I1 is of different values. When I1 is 0, the sum of I2 and I3 should be k. Based on the second step, the size of A0 is k plus 1. Similarly, when I1 is 1, the sum of I2 and I3 should be k minus 1, and the size of A1 is k. When I1 is 2, the sum of I2 and I3 should be k minus 2, and the size of K2 is k minus 1. So for any j in the set of 0 to k, when I1 is equal to j, the sum of I2 and I3 should be k minus j, and the size of Aj is k minus j plus 1. Then for the case when n is equal to 3, the set of A is the union of the disjoint sides A0 to Ak. We find the size of A in this case is the summation from 1 to k plus 1, which is equal to k plus 1 times k plus 2 by 2. Combined with the size of S, which is equal to k plus 1 cubed, the final probability is given by k plus 2 by 2 times k plus 1 squared. We see the final result is not equal to 1 over k plus 1, but the deduction for every possible n is with no n's. Is there a general formula for any n greater than or equal to 1? We introduce a trick called stars and bars here. Before the introduction of this method, we first assume the concept of binary sequence. First, we write down a binary sequence of C zeros and D ones. For example, when C is equal to 3 and D is equal to 6, we can write a binary sequence 1 1 1 0 1 1 0 1 0. Second, we distinguish the zeros by an additional label from 1 to C. For example, for the sequence above, we label the 3 zeros with 1, 3, and 2. Third, we distinguish the ones by an additional label from C plus 1 to C plus D. For example, for the sequence above, we continue to label the remaining 6 ones with 4, 6, 5, 7, 8, and 9. All the labels give a permutation of 1 to tier C plus D. So the number of permutations is C plus D factorial. In the second step, we have c factorial ways to assign labels. In the third step, we have d factorial ways to assign labels. If we suppose there are b of c d ways in the first step to write the binary sequence, we have c plus d factorial equal to b of cd times c factorial times d factorial. Based on the equation, we get b of cd equal to c plus d factorial divided by c factorial d factorial, which is equal to c plus d choose c, while n choose k represents n factorial divided by n minus k factorial times k factorial. Note that n choose k is actually the binomial coefficient, so generally, if we want to get a binary sequence with c zeros and d ones, there are b of cd ways. Then let's go back to the original problem with n equal to 4 and k equal to 6. We write down a sequence of k1s and n minus 1 zeros. For example, 1 1 1 0 1 1 0 1 0. Next, we replace zeros by comma and consecutive ones by their sum. So the first 3 consecutive ones become 3. The first 0 becomes a comma. The second 2 consecutive ones become 2. The second 0 becomes a comma. The third one is still 1. The last one becomes a comma. We add a 0 in the end. This gives the desired outcome since 3 plus 2 plus 1 plus 0 is equal to 1 plus 1 plus 1 plus 1 plus 1 plus 1 plus 0 equal to k. The sum of the integers is k. That is all we want in the problem. So given a desired outcome, the above procedure can be reversed to give a binary sequence of k1s and n minus 1 zeros. That means for n equal to 4 and k equal to 6, the size of A is b of n minus 1k. We conclude that the number of desired outcomes is equal to the number of possible binary sequences. Why could we get to this conclusion? We use bijective proof to show this. If f A to B is a bijection with finite domain A, then the size of A is equal to the size of B. So the final result for the probability of A is given by B of n minus 1k divided by the size of S, k plus 1 to the power of n, with B of CD representing number of binary sequence with C zeros and D ones. Okay, this is the end of the video tutorial. You can now apply the counting tricks we have introduced to the questions in the question list.